This is an example of an AC Mesh Solutions game in Circuit Tutor at level 1. So go into the AC Mesh Solutions game. And we do have examples available here in multiple levels of difficulty, so it's generally a good idea to look at some of those prior to starting the problems. In this case, I'm just going to go straight into a problem at the easier level 1. Okay, so we do have some written instructions here if you need those. And you can pull those up at any time just by clicking on the help button here. Now, as it points out here, in the solution game, they are giving us the KVL equations. So in this case, for a level 1 problem, all we need to do is to write a sought variable equation for the sought. In this case, it's the sought current. Okay, and as I was pointing out, the help button will bring up that help at any time. Okay, so let's go ahead and write that sought variable equation. And again, this is a branch current going through a single element. So it's a sought branch current. And so that will be fairly simple. We have I naught equals. And now we see that there's only one mesh current. The mesh currents have been automatically labeled for us here. Notice that by default it does take the reference mesh to be the outer mesh here, which is, so therefore the outer mesh current is not shown, the one that would go counterclockwise here. So we see that a single mesh current, since the outer mesh current has been defined to be 0, being the reference mesh, the single mesh current only goes through this resistor and does so clockwise, which is going up, therefore, in agreement with the direction of I naught. So therefore, I just need a single mesh current term here. We don't subtract, for example, I0, the reference mesh current, because that's just not done. So that would just be equal to I1. Now, again, if this current arrow were pointing down, then we'd have a minus sign there. So it's always important to check the polarity to get the correct answer. Okay, so that equation is correct, and now we've written all the equations that we need for this problem. So we'll click No More Equations. And now the new part in a solutions tutorial is that we're going to actually try to solve these equations so we can eventually get the sought variable, which again is just really I1. And to do that, we're going to put these equations first into a standardized form where we put all the constants on the right-hand side and combine, for example, all the I1 terms together and all the I2 terms and so forth to put them into standard form and make it easier to solve. When we're doing that, we are allowed to multiply through by a constant, although I don't think there'd be much reason to do that here. But you are not allowed to make any substitutions. In this case, there would be nothing to substitute anyway, but we cannot combine these equations, for example. Okay, so we'll enter the first equation. We have 2 rows here, one for each equation. The sought variable equation is not entered into this form. That will be used later. So the first equation, we see for the I1, we have a value of 1, and then we have a value of 6 over here. So the real part would be 7. And then we also have a J7 coefficient, so that would be 7 plus J7. Notice that the coefficients here on the left-hand side of these equations are entered in rectangular form, hence the single text box. And these are generally complex numbers, so they might be real. And the ones on the right are entered in polar form. And the reason that's done is simply because that's usually more convenient based on the original form of these equations. Okay, so that's the I1, and then the I2, we see we just have a minus 6. So we just put minus 6 there. And then on the right-hand side, we're going to bring this constant over to the right-hand side by subtracting from both sides. And so we would have a negative 1 angle 120. But let me point out, however, if you tried to enter negative 1 here, for example, that will not be accepted. And the reason is that this is simply the magnitude of a complex number, and by definition, the magnitude of a complex number is always a positive number. It's the distance from the origin in the complex plane. It cannot be negative. Therefore, as it explains here, to form the negative of a complex number, we're going to change the phase angle by 180 degrees. We can either add or subtract, but we do want to keep the angle in the range from negative 180 to 180. If we try to go outside that range, it will not be accepted in Circuit Tutor. So here it would be 1 be the correct magnitude to enter there. and then subtracting, well, remember this is actually going to be negative 180, so then we have to subtract 180 from 120, giving us negative 60 degrees. Okay, and remember that in polar form, negative 1 is simply one angle 180 degrees. That's why we use that 180 degree phase shift. As you can see on the Argon diagram, if you draw the real axis and the imaginary axis, negative 1 would be over here to the left of the origin, and therefore the angle there would be 180 degrees from the positive real axis, which is how you measure the angles. Okay, so for the second equation, we look for the coefficients again of I1, and there's only one term here, so that would have a negative 6 coefficient. And then for I2, we see that we have a 6, and that part's imaginary, and a 9, which is real, so we're going to have a 15, 6 plus 9. And then we have minus J2, which is the imaginary part of the coefficient. So we combine those into a single complex number just by adding the different numbers together. And then again, we're going to have to bring this over to the right-hand side, so that will become 5 angle 0 on the right-hand side. So we just enter that directly as 5 angle 0. So that should be finished. And that is correct. Now, the simplified equations are printed here on the screen for us. And the next step, even though we're probably not going to use matrix methods really, is just to show how these can be written as a matrix, just for illustration purposes. And so we're going to cast these into a matrix equation. And that's actually very easy here because all you have to do is click a single button and it'll copy those coefficients for you. I mean, you could retype them if you wanted, but it's easier just to press the button. And again, these are still shown in the same form as they were here. And remember what this means is each row of the matrix equation is the same as one of the simplified equations. So this means 7 plus J7 times I1 minus 6 times I2 is equal to 1 angle negative 60 degrees. That's just the first equation using the standard rules for matrix multiplication. And then the second equation, just negative 6 times I1 plus this coefficient times I2 is 5. So that would be the second equation. So we'll check that. And of course that's correct. And now the next step is we're going to actually solve these equations. Now, again, in complex number case, I would really not recommend probably doing it as a matrix. I mean, it is possible to do this, for example, in MATLAB. And there are sometimes calculator programs that can do this, or you could do it in an online calculator. But really, your instructor may expect you to do this on an exam, for example, in which case they may not allow you to do that type of thing, and they may want you to do it by hand. So that would really be up to your instructor as to what they expect, so you could ask them. But I'm going to show you how to do it by hand, because for a 2x2, really, that's quite easy, or at least relatively easy to do. It's certainly harder than doing it with real numbers, but again, the algebra with complex numbers is really done exactly the same way as you would do elementary algebra with real numbers. It's just that we now have a complex number, and we have to do complex number arithmetic, which is certainly a little bit more complicated than doing it with real numbers, but it's the same exact principles that we would use to solve. Okay, and your instructor might ask you to turn in the handwritten algebra work that you do. If so, then retain that and turn that into them on request. And if not, you might want to keep that just really for your own records. So when you're studying, you have a record of how you did the complex algebra so you can remember how to do that. Okay, so now we need to enter simply the results of I1 and I2 into the form. Now, I will point out you could, if you didn't want to do all that, you could skip this and go straight into entering the value of I0, the sought variable, which is identical to I1. But I usually like to check the individual values first just to make sure that we don't make a mistake. So I'm going to go back and I'm going to do the algebra here on paper. So I've written this out for you. And first of all, I'm just going to basically copy these simplified equations over. So we have the 7 plus J7 I1 minus 6 I2. I put bars there to indicate complex numbers, which you can do if you like, is equal to the 1 angle minus 60. And then the second equation inside this bracket here is just negative 6 I1 plus this coefficient I2 bar equals 5 angle 0, which for short we can just write that as 5 in rectangular form. So there's various ways to solve a 2x2 system, as you learned in elementary algebra. I could solve this equation for I1. For example, I just add 6I2 to both sides and then divide by the 7 plus J7. And divide each term here by that number using a complex number calculator, and then divide by the -6 to solve for I2. So that would be one method, or you could alternatively, and then, I'm sorry, when you've solved that for the I2, then you would plug that in to the second equation here, and that would give you a single equation in a single unknown, namely the I1. And by combining the coefficients of the I1, then you could take all those coefficients and divide them into the right-hand side, which is just 5. And again, using a complex number calculator, you could then find the I1. And you could also solve this for I1 if you like, or solve it for I2. It doesn't matter, and plug in here. Either way, you'd get a single equation in a single unknown, or you could solve this equation for either variable and plug that back in here. So either way you do it, you're going to get the same result. I'm going to do something which is similar, but a little bit more like Gaussian elimination. So what I'm going to do is I'm going to actually multiply this entire second equation by a coefficient which is equal to this coefficient divided by this one. And when I do that, obviously the -6's will cancel out here and just give me the j7 plus j7 rather, I1, which means that this one will equal to this. And then if I subtract those two equations, that will entirely eliminate the I1 term, giving me the I2. And so it's kind of equivalent to the other methods, but it's just, I like to do it this way. So, so let's do that. And of course, when you multiply through by this constant, obviously we do have to multiply, as you always would in algebra, every term in the equation by the same constant for that equation to remain valid. Otherwise, of course, it would no longer be true. So when we do that, the I1 terms we know are going to cancel the way we've constructed this, so we don't even need to do that. For the I2 terms here, first we have the -6 I2, so I've factored out the -6 and put the I2 over here. And then we subtract the 15 minus j2, multiplying now by the 7 plus j7 divided by -6. And since I'm subtracting that, as I did here, the two minus signs cancel out. So I've just marked those as canceling. And that's my coefficient of the I2. And then on the right-hand side, I have the one angle -60 degrees here. And then I have to now subtract the 5 times 7 plus j7 divided by -6, which is what I did here. And then after subtracting that, I just canceled those two minus signs to make them pluses, just to make it easier to enter on the calculator. And now the next step would be to evaluate each of these expressions using a calculator that can do complex numbers. So I'll just illustrate some examples of that. So I'm using a TI 84 Plus calculator emulator here. And one of the important things here is I need to make sure that I am in complex mode, because if you're in real mode, you can't do numbers, or can't do calculations with complex numbers rather. So I can see right here that that is in polar mode, so that will give me answers in polar form. And I've also in the degree mode, since I'm in polar form, the angle measure matters, and I need to be in degree mode. If I wasn't in the right mode, I would go and set the mode originally by going down to here and either choosing rectangular or polar as I desire. And again, you'd set the radian or degree mode here. Since I've already done that, I'll just exit. And so let's, for example, evaluate this first expression. So just for simplicity, I'm going to enter the second part first, I think. So let's do parenthesis 15 minus, and now for the j, we have to put I in a calculator. That's the notation they use. And that's the second plus the decimal point here. That's the I, as you see there. And 15 minus I 2, and using implicit multiplication. And then I close parentheses. And of course, we do have to always put parentheses around a complex number here to multiply it by something else. Otherwise, order of operations would not multiply the entire expression. So then I'll put that times parentheses 7 plus j7. So that's going to be 7 plus I7, close parenthesis, and then divide by 6. And then I can just subtract the -6 there. And by order of operations, I don't need parentheses for that, because multiplication and division, of course, are done before the addition and subtraction, as you know in algebra. So, and if you want to put parentheses, of course you can. It won't matter. Okay, so we press enter there, and that will give us this number 20.53 to 4 significant digits. And this angle now is in degrees because I'm in degree mode. So this would be 47.63 degrees times I. Because remember, that's a different form of the polar form of a complex number. So I just wrote it here using the angle notation. And then we can similarly evaluate this term. And so, well, why don't I do that just to demonstrate? Now, there's a little trick here when we're entering in polar form. So I've already entered a variable e to help me do that, which is little e to the I pi divided by 180. And I stored that then using the store key in variable e, which is the alpha e here. So I'm just going to recall that by going alpha e. And then I have to raise that to the power of the degree, which is the negative 60 here. So negative 60. And then exit the exponent. And then I want to add to that 5. And notice I did use implicit multiplication there, which is permissible, on this calculator at least, times 7 plus I7, close parentheses, again divided by 6. Or I could have probably just computed that in my head, but in any case, that should be it. And now I just push enter. And then that gives me the right-hand side, 8.049, angle 38.11 degrees. Okay, and then I can just divide these two. So I could take, for example, my answer here and divide that by this. Now, I can't type it the way it's written here. That's the odd thing about this calculator, is that it won't accept an input written in the same format as the output. So I would have to and I have to use parentheses because I'm multiplying these two things in the denominator, and if I want to divide by both of them, it's crucial to use the parentheses. So I'm just going to retype that as 20.53, and then I have the e to the power 47.63, and then exit that, close parentheses again. If I didn't use the parentheses there, I'd get the wrong answer, because then I'd be basically multiplying by this the e to this power, rather than dividing. So very crucial to use the parentheses there. And that answer on this calculator just is this last computed value. And that, even though it won't accept it if I typed it that way, it will accept it when you use the internal answer function. So that will give us the answer of 0.3921, angle negative 9.52 degrees. So I've just written that here. And now I need to plug that back in. I can choose either of these two equations. I don't need the multiplier anymore to solve for I1. And so I've just used the second equation here. So I took the 5 and I subtracted off this term, which, since I know I2 now, so I subtract the 15 minus J2 times the value of I2, just copied down here. And then to solve for the I1, I just divided by negative 6, since that was the coefficient of I1. I mean, you can do that in 2 steps if you like. I just did it in a single step. And again, we enter this on the calculator. I think I've already illustrated how to do that, so I'll just show you that the answer came out to 0.3118, angle negative 68.99 degrees. So now we have the two values, and we'll go back to Circuit Tutor to enter those into the form. So I1 is the 0.3118, angle negative 68.99. And again, I try to use 4 significant digits to avoid problems with round-off error. And then the I2 is 0.3921, and the angle negative 9.52 degrees. Yeah, probably 2 digits past the decimal point is sufficient for degrees usually. So, and then I'll just check those, and that's correct. And now the last step is to use the sought variable equation, which basically just means entering I1 as I0. So that doesn't require any computation. So I just basically, I'll just copy that. So that's the value of that again, rounded off a little bit. And we'll check that. And that is correct. And now that's printed on the screen. And then the last step here is to do an inverse phasor transform to actually find I0 of t in the time domain. So that's really the ultimate objective here. And so we need the inverse phasor transform. And remember, that's fairly simple to do. The one part here, remember, I have to use a cosine function. Now that's shown here for you automatically, but you want to make sure you remember that, because when you do it on paper, you would have to remember that yourself, that phasors are always based on cosine, not on sine. That's just something you have to learn. And the omega here is given for us. It's 40 kiloradians per second. The text box here will not accept a metric prefix. It'll show you an error if you try to enter that. So instead, we just enter 40,000. And then the phase angle will be the phase of the phasor. So that's just negative the 69 degrees. And then the magnitude would be the 0.3118. And we'll check that. And that is correct. So that essentially completes the problem. If you do want a detailed explanation of, for example, how these KVL equations were derived, or the slot variable equation, which in this case is pretty simple, you can just click yes there, and it'll offer more detailed explanations of these things. And in particular, you can get a very detailed explanation of each KVL equation if you would like to look at that. And that does complete this problem.